sp3 hybridization. The example is methane molecule, which was not being explained with the help of simple overlapping theory of pure orbitals. Now in methane, carbon is the central atom and hydrogen are the surrounding atom. So as usual, we will find the valence shell, ground state configuration, of carbon. Carbon is basically 6 electron, 1s2, 2s2, 2p2. So valence shell configuration is 2s2, 2p2. It comes equal to 2s2, 2p2. And with the electronic configuration, this 2s2 and this has 2p2 according to Hund's rule. However, this is unable to explain the tetravalency of carbon, and thereby in excited state configuration, valence shell configuration, carbon makes this one of the 2s electron to migrate in 2p. Configuration is 2s1, 2p3, and it has 4 half-filled orbitals. That means it is now having the possibility of getting its tetravalency or 4 bonds. Mixing of s orbital and 3 such p orbital will involve the hybridization, that is sp3 hybridization. Now in sp3 hybridization we have this sp3 with one electron to each orbital would be named as sp3. The bond formation with 4 carbon, 4 hydrogen, this is all the sp3 hybridization of carbon. All orbitals are sp3 directed tetrahedrally, and these are the bonds, electrons shared by hydrogen. As a whole, the shape of the molecule is tetrahedral. It is not in a plane, and the bond angle is 109 degree 28 minute, or in rough it is 109.5 degree. 30-minute means it is exactly 0.5, so it is nearly equal to 109.5 degree. The structure is, this is central carbon, these 2 are 2 hydrogen, this is another hydrogen, and this is another hydrogen. The bonds are like this. So when we join the structure with imaginary lines, we will get a tetrahedron with bond angle 109.5. Now it clearly states that these are not in a plane. The structure is made as this is the central carbon, the 4 valencies are being joined to 4 hydrogen, and that makes it a tetrahedral molecule. This is central carbon, and this are all the hydrogen. All the bond lengths are equivalent and all the bond angles are 109.5 degree. Now in this structure, this tetrahedral structure, this is evident that it is not in a plane. It is a 3D geometry, keeping one triangle over here, one triangle over here, another triangle over here, another triangle over here. It gives a closed figure, closed structure. This is how the tetrahedron is being made. This is the structure of methane. In case we want to make a structure of ethane, we are having 2 carbon with each one as sp3 hybridized one. So this is also another sp3 hybridized carbon, and there will be a carbon-carbon bond prevailing between this 2 sp3 hybridized carbon. So this is how we are adjusting the ethane molecule. This, the 2 carbon-carbon, each one is sp3 hybridized, and then one is the sp3 hybridized orbital of carbon, another sp3 hybridized orbital of carbon. These two have overlapped to form the carbon-carbon sigma bond, and this is the overlapping of sp3 hybridized orbital and s orbital of hydrogen. That is the overlapping of a hybrid orbital of carbon and pure orbital of hydrogen. That's how CH bond is being formed. This is also a sigma bond. Means a sigma bond could be formed by the overlapping of 2 pure orbitals, by the overlapping of 2 hybrid orbitals, or by the overlapping of 1 pure orbital and 1 hybrid orbital. So this is how the structure is being made. Since carbon is having the bonds of single bond, double bond and triple bond, in case carbon is having all sigma bonds, the carbon will be sp3 hybridized always. The next hybridization is sp3 dehybridization, that is the involvement of d orbital. The example we will take is phosphorus pentachloride molecule. This also was not being explained as per this octet rule. It is the phosphorus is superoctet or hypervalent one. Now having this configuration of phosphorus, the valence shell, ground state configuration of phosphorus. Phosphorus is 15, that is 1s2, 2s2, 2p6, 3s2, 3p3. This is the valence shell configuration. 3s2, 3p3, and since 3 is having another d and no electron is there, it will be 3d0. The orbital diagram is 3s2, 3p3 according to Hund's rule, and 3d, the 5 orbitals would remain vacant. Now from here it is clear that phosphorus has to form 5 covalent bonds through the mutual sharing of electrons, and for this phosphorus need 5 half-filled orbitals. Here in the ground state we have only 3 half-filled orbitals. So in excited state, as chlorine approaches phosphorus, what will happen? The electron-electron repulsion will increase the potential energy of phosphorus, and thereby one of the electron of 3s will migrate to 3d. So in excited state configuration, this will be 3s1, 3p3 and again 3d1. One of the electron is migrated from 3s to 3d. Now we have 5 half-filled orbital s, 3 such p orbitals and 1 d orbital. So it will intermix together and will undergo our hybridization, sp3 dehybridization. Mix 5 hybrid orbitals, as the number of pure orbitals involved is equal to the number of hybrid orbitals formed. This is all sp3d, and we have 4 3d orbitals pure, but no electron would be there. And in each sp3d we will have single electron. These 5 electrons are filled up in hybrid orbitals of phosphorus. In the next step we will have bond formation. With 5 Cl atoms. This is the sp3d hybridization, hybrid orbitals of phosphorus. D pure orbitals vacant, and we will have the overlapping of 3p5, that is the pz orbital of each chlorine with the sp3d hybrid orbital of phosphorus. It makes the formation of 5 phosphorus chlorine bond. The shape is known as trigonal bipyramid. Bond angle is 120 degree as well as 90 degree. Let's see how the shape is actually. This is phosphorus. In the plane we will have 3 Cl, each with bond angle of 120. This is in the plane. Just like the sp2 hybridization planar trigonal, these 3 are there, and it is just like I gave the example of fan lobe and the fan blades. One chlorine is just above the plane like this, and one chlorine will be below the plane. So I am showing the chlorine like this. One chlorine above the plane, one is below the plane. It's obvious that these angles are within plane, the angles are 120, but this will be perpendicular to the plane. So this is above the plane is 90, even below the plane is also 90. Thereby it has 2 different bond angles, and hence what we can say that the PCl bonds in PCl5 molecule are not equivalent. The bonds that are perpendicular to the plane are called axial bonds, and the bonds in the plane are known as equatorial bond or planar bonds. So it's obvious that planar bonds and axial bonds are of different bond angles and hence different bond strength. So these are not equivalent, and hence what we could say that PCl5 is not a thermally stable molecule because only of its non-equivalent bond strengths. And if therefore we heat phosphorus pentachloride, it is a reversible reaction. It changes to PCl3 and readily leaves this to axial chlorine. So this reaction is quite feasible because of this non-equivalent nature of all 5 phosphorus chlorine bonds in PCl5.